Hi, everyone. Welcome to the second session on climate change effects on groundwater resilience regarding pollution and remediation. My name is Tibor Stigter, and I come to you from IHE Delft in the Netherlands. And I'll be co-chairing this session together with my dear colleague Jared van Rooyen. He's from Stellenbosch University in South Africa. So great to have you with us, Jared. And besides introducing the speakers, we will especially be looking at all the questions that you have in the audience and that you can submit through the Q&A box, which is on the bottom of your screen. Now, of course, we do encourage you to submit as many questions as you can. We won't be able to maybe answer them all during the session, but we will definitely come back to all of them in written. So we will ask the speakers to respond to your questions throughout the session and afterwards if needed. Well, of course, I would like to welcome our 7 speakers of this session, coming to us from 3 different continents. So good evening for some and good afternoon, good morning. The focus of today's session actually is very nice. It's on how we can use adaptation solutions, such as managed aquifer recharge, to increase the resilience to groundwater pollution, which we of course know is largely man-induced, but it can also be further affected under climate change, and we need some of these solutions to help increase or build on the resilience that groundwater naturally has. So without further delay, I would like to invite Jared to invite the first speaker of the session. Please, Jared.
Good morning, everybody. Thank you so much for having me. Our first speaker this morning is Mahmood. He's also from IHE Delft. I'm very excited to hear what she has to say. And she'll be presenting on managed aquifer recharge as a source of emergent pollutants in the Korba aquifer in Tunisia. So Ms. Hafsa, on to you, and very excited to hear your speech.
Hi, everybody. First of all, thank you so much for having me here. I'm going to talk about the topic managed aquifer recharge as a source of emerging pollutant in groundwater. Next slide. So the motivation for us to work on this topic was to focus on the key issues of water scarcity and climate change. As in future, we know that surface water variability will be very high relative to the groundwater. So groundwater will be a much more promising resource in that scenario. And new technologies like using treated wastewater to recharge groundwater are very essential nowadays if they are done in an adequate and appropriate way. But if there's no proper monitoring and management, it can be a source of bacterial, chemical, or emerging pollutants. Emerging pollutants are those micro pollutants that have the ability to bioaccumulate and biomagnify through the food chain, and they, even in very low dose, can be harmful for the organisms. Next, please. So my study area was northeastern part of Tunisia, and it has a climate of semi-arid to arid, and in this area, basically, it's a coastal aquifer, and the main activity of this area was agriculture. So there is a huge abstraction of the groundwater and huge dependency on the groundwater, because of which there was saltwater intrusion happening previously. And that's why in 2005, the government decided to establish a managed aquifer recharge site, which composed of 3 basins. They were applying recharge on 2 basins at one time and using hydraulic loading cycles. But they were also recharging it with the treated wastewater. So it was seen that there were some studies that observed that there's nitrate concentration increasing in the groundwater, but there were no research done for the emerging pollutants, and that's why we were planning to focus on that. Next slide, please. So our objective was to first evaluate the effectiveness of managed aquifer recharge in Poralai Aquifer, and to also identify what are the current risks which are imposed by managed aquifer recharge of emerging pollutant in specifically the unconfined phreatic Poralai Aquifer, which was mainly plioquaternary aquifer. Next, please. So we basically took almost 30 wells in the central Poralai region where the MAR was present. And we also, for the pharmaceutical analysis, and we also took the samples from the effluent of the treatment plant, which was supplied to the MAR site. And our selection of the pharmaceuticals were basically based on what pharmaceuticals were previously found in the effluent of the treatment plant wastewater, and what are the pharmaceuticals which are mostly most commonly used in Tunisia for human purposes. So our first step was to do the pharmaceutical analysis. We did it by using the solid phase extraction, reversed phase hydrophilic liquid chromatography with mass spectrometry. Then we did groundwater flow modeling by using the solver ModFlow NWT 2005, as there was a huge variation in the elevation within small distances. So ModFlow NWT was used, that's why. And then the next step was to do the conservative solute transport modeling, MT3DMS. And we basically wanted to study the plume spread, how it is currently after 10 years of application of MAR, and how it will be for year 2100 based on climate change scenario RCP 8.5. Next, please. And we chose carbamazepine for the conservative solute transport modeling because it has a very low degradation rate. So it can point out the pollution, old pollution. Next, please. For that purpose, we did a lot of field work specifically for the groundwater flow modeling. We did riverbed conductivity experiments, all the physiochemical, conventional physiochemical lab test for the groundwater as well as the effluent. Next, please. So the results showed that in the treated wastewater, we found the concentrations of ethanol and carbamazepine, whereas roxithromycin, caffeine were below the limit of quantification and below the limit of detection. Whereas sulfamethoxazole was not at all detected in the effluent of the treated wastewater, even though in previous study it was found that there was some concentration of sulfamethoxazole in treated wastewater of Poralai Aquifer. Next, please. So based on the results of the emerging pollutant in groundwater, we found that sulfamethoxazole concentration was still present in the groundwater, and there were some parts, even though it was not found in the effluent of the waste treatment plant. So it was indicating that there was some past pollution which is still present in the groundwater, as well as in some cases it was because of the urban pollution source. In case of carbamazepine, the concentrations were present, and there was a plume which you can see from the readings, but that concentrations were tenfold lower, which indicated that there's a lot of absorption happening in the managed aquifer recharge site, as carbamazepine has a very low solubility in water. Next, and other pharmaceuticals were not detected in the groundwater. The ModFlow results of hydraulic heads before and after MAR showed that there was 1 meter difference in the hydraulic head. 1 meter head was improved after the application of MAR. Next, please. The area of influence was almost, you can see in purple, and so the contribution by MAR was almost 0.24 millimeter cube per year, whereas 2.7% of the saltwater intrusion was being reduced every year by the application of managed aquifer recharge. Next, please. And the conservative solute transport modeling results showed that the plume spread currently is exactly in the same area where we found the concentrations of carbamazepine. And it was almost 9 kilometers square in total. Whereas in year 2100, according to the RCP 8.5 scenario, the plume is expected to increase to almost 16 kilometers square. Next, please. So I would like to conclude my presentation by saying that the MAR it does contribute to the replenishment of the aquifer and seawater intrusion, but the expansion of MAR on large scale is required to see significant and substantial results in replenishment of the aquifer. Apart from that, as we saw that the emerging pollutant concentrations were tenfold lower than what was present in the treated wastewater. So it's obvious that there is a lot of absorption happening in case of carbamazepine and degradation happening in case of the other pharmaceuticals. Which means that we need to focus on in future research for the reactive solute transport modeling to understand better these processes. And apart from that, we need to focus on what concentrations are found in the soil of the emerging pollutants, because it's also one of the major reservoir for pharmaceuticals and emerging pollutants. Next, please. I would like to just thank all the research team and staff of the chemistry laboratory and education laboratory at INGRIF, Tunisia, my research team at United Nations University, UNU Flores, and my research team and my teachers and mentors of TU Dresden. Thank you very much.
Thank you very, very much, Hafsa. Very interesting study, and again, further also, developing on work and the importance that John Cherry's talk mentioned yesterday on passive remediation, which I guess here would be extremely important regarding these micropollutants. We'll try to save the questions to the end, given the time limit that we have. So throughout the coming minutes and hour, these questions will come to us, I'm pretty sure, in the question and answer. So with that, I would like to follow with the next speaker, and that is Sikander, who is with us. Sikander Hayat from the Utrecht Lorent University Department of Geology in Hungary, and well, your talk will be on site suitability mapping for managed aquifer recharge implementation in Poralai and Hangol, the coastal basins of Baluchistan, Pakistan. So please, Sikander, the floor is yours.
Thank you very much. My topic is Managed Aquifer Recharge Suitability Mapping in Poralai and Hingol. These are the two coastal basins of Pakistan. Next, please. So here we have the map of Pakistan, and this is the gray area here. Is the largest province of Pakistan, the southernmost, and we choose the two coastal basins. Why we chose them? First reason is that groundwater level is declining very rapidly. In past 5 years, it has been declined 4 meters. And the main reason is, first reason is migration, rapid increase in population because of the immigrants, war-related immigrants from Afghanistan, the neighboring country, and the other is that in the future we have the projections that population is going to increase here in the coastal areas because of the construction of China-Pakistan economic corridor. It's a huge project. And the second point is that soil erosion is very high in this area because of the overgrazing. Most of the people have nomadic lifestyle, and cattle are the main livelihood. So overgrazing is a big problem, which has been intensified by the changing patterns in precipitation. Rainfalls are intense and for short duration, so percolation is low and erosion is very high. And the third reason is saltwater intrusion. And saltwater intrusion is there are a couple of factors, including global sea level rise, over abstraction of water on the coastal wells, and reduced precipitation. Next slide, please. There are a few methods that are already being used in Baluchistan, but not in our basins, and these are very successful, including ditches, terraces, trenches, and especially leaky dams. They are very useful. One method that is delay action dam. In 1995 to 2000, there are around 300 dams were built, but they were failed because of over deposition of sediments, and they silted up very quickly, and they were not successful. But after that, they planted some plant species, non-palatable plant species, and in 3 to 4 years, sedimentation is reduced to 50%. So now they are repurposing it by building inverted wells in the downstream part of these dams. Next, please. So I already mentioned why we choose these two basins. This is the location of our two basins. Next, please. So we started with the NOVAS platform and our suitability mapping. So first we chose the Mars method selection, and there are 5 options here: source of water, soil type, land use purpose, and typical scale. And we put all the conditions of our area, and Mar gave us 6 methods. Some of them are suitable and some of them are not suitable based upon the geological and climatic conditions of the area. For example, dune filtration is not suitable because we don't have sand dunes here. Subsurface are not suitable because depth to the bedrock is really deep, and water table is 15 to 30 meter deep. So these flooding, trenches, ditches and furrows, and rooftop harvesting in the urban areas are suitable. And leaky dam is also suitable. Method is not given by the NOVAS, but is already being used in Baluchistan, so it's also suitable. Next, please. So we applied the very well-established method, GIS multi-criteria decision analysis. First step is defining a goal. So our goal is to search for a site for MAR implementation, suitability mapping. And then the constraint mapping are screening of suitable areas. So areas more than 40% slope are considered unsuitable for MAR, and the urban areas. And then the selection of criteria. It depends on how important these criteria are and how much data we have. This is a remote area. We don't have very detailed data, but we have data for geology, soil, precipitation, land cover, and drainage density. So we use these 6 criteria. And then we use multi-influence factor method to give the importance to each criteria, how important is different criteria. Then common scale, different criteria have different units. So we give them scale from 0 to 1, 1 most suitable and 0 not suitable. And then finally, weighted linear combination is used to overlay the criteria to find and rank suitable areas. Next, please. So here are 2 constraint maps, first for slope and second for land cover. And black are not included in the study. Here also, the urban areas in black is few, but they are not considered in the study. Next. So multi-influence factor method is based on the relative importance of each factor and how each factor is influencing the other one. For example, geology is influencing soil, influencing drainage density and managed aquifer recharge. So it got 3 points. And slope is affecting drainage density, managed aquifer recharge, and minor effect on soil. So it got 2.5 points. So that's how we calculated the weightage of each factor. Each criteria, the sub-criteria is given the ranking from 0 to 1 based on how suitable it is. Next. So here are our 6 maps. The first one is geology. Here we have alluvium. Here we have mixed, in purple we have mixed shale, and in yellow we have limestone. And then we have terrain slope, soil map, land cover, and drainage density map and drain map. Next, please. So final map is produced by weighted linear combination method, and it shows us that Poralai Basin is suitable for application of MAR methods, and Hangol Basin is few parts are really suitable and others are moderately suitable for the application of MAR. Now there are certain restrictions to that. First is the quality of groundwater. For Hangol Basin, according to government of Pakistan, it is quality is good for recharge, but for Poralai Basin, we don't have any data and further studies are needed. And this GIS analysis is just to narrow down our focus on the suitable areas, and it's no way intended to make the decisions to construct the mass structures. Next. So MAR is really useful, and delay action dams were not successful but effective. And MAR, along with effective landshed management, watershed management by plantation different kind of plant species, would be more effective. And the Innovas platform is really useful to narrow down the MAR method. But if under the MAR method selection, temperature of area, precipitation, depth to water table is included, so it would be more specific and would further narrow down the results. So yeah, these are my results. Thank you very much.
Thank you very much, Sikandar, for a nice talk. Indeed, nicely showing the potential of these kind of suitability mapping techniques to let's say find the best areas for upscaling pilot cases, for instance, of MAR, but needing, of course, then additional analysis in the field. There is some time for a question or two. I would first pose a quick one. What would, in your case, be the main source of your MAR? Is it the flood runoff
Yes.
that you consider? Yeah.
Yeah.
Okay.
Runoff water.
But which is of course still a challenge given the deep water table. But you mentioned
Yes.
that already. Jared, is there any other question that either you or the audience is posing?
Yes, Tibor, there is one question from the audience. Falak Iqbal asked, he has a question due to the recent rainfalls in the area in Pakistan, and he'd like to know if you understand that this helped recharge in the aquifer, and if it did, then why, and if it didn't, is it significant, or vice versa?
The thing is that these we have rainfall. I already mentioned in the beginning, these are very for short period and very intense, so they are causing flash floods. We need some kind of structures, for example, leaky dams that can reduce the flood intensity plus recharge. So we need to interfere with the natural process somehow to make them useful.
Okay, so just to clarify the question, he wanted to know specifically if the recent rainfall has changed the recharge dynamics in the region, or if this is significant or not, I suppose.
I have no idea about that this recent in past year. Sorry.
Okay, thank you, Sikandar.
You're welcome. Thank you very much.
Yes. I guess it is something that with future climate change, at least what we expect in terms of more intense rainfall events, focused recharge, which also Richard has talked so much about, would be so important. So we could try to find ways of using that in setting up our MAR techniques, and perhaps Enrique will talk a bit about that later as well. Thank you very much again, Jared. I would like to invite you to invite the next speaker to the stage.
Yes, of course. Our next speaker is from Botswana, which is really close to where I am. I'm very excited. Her name is Rankgomo. She's an MSc candidate from the Pan-African University Institute of Water and Energy Sciences, which also include climate change studies. And she'll be presenting to us today on assessing the potential of an artificial groundwater recharge, a case study from the Palla Road wellfields in Botswana. So I'd like to invite Khontle, and I'm very excited to hear your talk.
Thank you very much. Greetings, ladies and gentlemen. I would like to take you through the findings of assessing the potential of artificial groundwater recharge in Palla Road wellfields, Botswana. Next slide, please. So firstly, I'll go through the outline of my presentation. I'll go through the effects on groundwater, the objectives, methodology, results, then the conclusion. Next slide. So on the effects of groundwater, 2.5 billion people worldwide depend on groundwater solely for their basic human needs. Also, groundwater accounts to about 30% of the total supply of fresh water resources. Groundwater resources, though, are limited and they are declining in terms of quantity as well as quality due to various reasons, including contamination as well as climate change. A brief background on Botswana is that it is categorized with a semi-arid climate. It has low rainfall and has high evapotranspiration rates. However, most of the country's anthropogenic activities depend highly on groundwater, which can lead to high abstraction and thus depleting aquifers. So Botswana's water security problems have thus put pressure on the available water resources, and this has led to the need for underground storage. So the Palla Road well fields were started, the drilling in the Palla Road well field started about 3 decades ago in the year 1987. And they have been studied throughout these 3 decades. In the year 2000, a water carrier pipeline from the northern part of the country to the southern part, which delivers water, was completed in order to provide water to the southern part of the country. In the year 2001, the Palla Road well fields were connected to this north-south carrier. However, this connection was through an intermittent water supply. So next slide, please. So I'll go through the objectives of this study. They are to identify and to assess the potential areas suitable for managed aquifer recharge in the Palla Road well fields, as well as to evaluate managed aquifer recharge potential based on the hydrological characteristics of the Palla Road well fields. Next slide, please. So I'll go through the methodology of this study. So the Palla Road aquifers are located in the eastern part of the country, in the Limpopo Basin, which is shared amongst 4 countries, that is Botswana, Zimbabwe, Mozambique, as well as South Africa. So the catchment area is denoted with the red color. This is where the Palla Road well fields are located in the study area. Next slide, please. This research was carried out based on special observations using dual model, the Q-SWAT plus model, as well as the soil water balance model, in order to assess the potential areas for managed aquifer recharge in the Palla Road well field. So this investigation was carried out for a period of 11 years, from the year 2008 to the year 2019. Next slide, please. So the results which were obtained from this simulation are as follows. As we can see in this figure, this shows the mean water balance of the catchment area. So the first column denotes the precipitation and the last column denotes the evapotranspiration rate of that area. So as you can see, the precipitation is about 400 and the evapotranspiration is about 390. So this shows that most of the precipitation is evaporated, and thus we can see from the second column, it shows the percolation rate. So there is less percolation in this area. Most of the water is lost through evapotranspiration. Next slide, please. Following which, this is a graph representing the precipitation and the percolation rate of this area. So it represents the year 2000, from the year 2009 to the year 2019. So a significant amount was recorded in the year 2009, 2014, and 2017. However, in the year 2014, that's where a significant amount of percolation was recorded in the aquifers. Next slide, please. So another set of results which were obtained are as follows, which have the recharge in the area in the year 2008, 2012, as well as 2016. So the right hand side of each figure shows the color which represents the amount of recharge in each area. So the first figure, which represents the accumulation to the year 2008, shows that most of the recharge was on the western side of the area. And for the year 2012, it was also on the western side, which is denoted by the light blue color on that figure. Now, as for the year 2016, it was most of the recharge was in the central part of that catchment area. Next slide, please. Therefore, based on the findings of this research, groundwater management is imperative in Botswana. Therefore, implementing artificial groundwater recharge serves as a basis to improve and to diversify the current available resources. Further investigation on this untapped alternative is therefore recommended. I would like to also highlight a quote by Lester R. Brown, which states that aquifer depletion is a largely invisible threat, but that does not make it any less real. Next slide, please. Okay, thank you for your attention.
Thank you very much, Grontje, for your nice talk on this interesting case study. We do have a time for a question or two. Jared, not sure if there are any questions on the Q&A or from your side.
There's no questions on the Q&A as for now, but just from my side, Grontje, I've had the privilege of being in the area and doing some work around southern Botswana. And okay. I think one thing that we found in a lot of investigations there is that a large proportion of the groundwater in the area is quite fossil and extremely old. But the accessible portion that people are using seems to be turned over quite fast in modern kind of climate scenarios. So looking into the future, do you expect that these kind of changing precipitation events are going to contribute to the potential for managed aquifer recharge in the area? Or do you think it could be a limiting factor considering the current recharge mechanisms in southern Botswana?
Okay, thank you very much for your question. Well, I believe that with managed aquifer recharge, we will be eliminating the evapotranspiration rate by deliberately harnessing that precipitation and inserting it into the ground for storage. So that will be eliminating the climate change impacts of low rainfall, affecting how the recharge is in the well fields.
Thank you very much. Yeah, I think it's a really good point, right? A lot of the water is being lost to evapotranspiration in the area. And if we could harness this, it's going to help promote development in the area. We know that water availability is a cornerstone of equity, especially in most of sub-Saharan Africa. So I think it's a great program and it's promising for Botswana's future.
Yes.
Thank you. Completely agree. Thanks for that question and your response, Grontje. I think in the sake of time, we will move on, and there will be room for more questions in the last part and the plenary of that we have at the end. But I would like to move on and invite Paul Pavelic. He's senior researcher from the International Water Management Institute, and he's currently based in Laos, if I'm not mistaken. And he will be talking about co-managing floods and droughts on the Gangetic Plain through a novel MAR approach. Paul, please, the floor is entirely yours.
Thank you, Tibor. Greetings, everybody. It's a pleasure to be here at this online conference. I'd like to talk to you about some of the research highlights from this pilot scale MAR study that we've undertaken on the Gangetic Plain in India, and specifically in the western part of Uttar Pradesh state. And before I do that, I'd like to just acknowledge my host of collaborators and co-authors on this paper, who come from IMI and other organizations in India, including TERI, LNRMI, CSSRI, and KVK, representing a whole sphere of different disciplines, because we've used a very multidisciplinary approach in doing this particular pilot scale evaluation. Now, as many of you all know, India is one of the champions in many respects in terms of managed aquifer recharge, particularly in terms of its policy attention and practical implementation. So what's different about this form of MAR that makes it novel? And I think the answer is that most of that effort has gone into the more drought-prone parts of the country, and there's very limited experience in the more humid flood-prone areas, where now groundwater depletion is also emerging as well. So with this particular form of MAR, we have an opportunity to deal with flood mitigation and groundwater depletion in one particular form of intervention. So that's the concept behind this particular trial. So next slide, please, Callum. And so, being a little bit different, we had to set about establishing the technical and non-technical performance and impacts of MAR in this particular setting, and that's the major aim of this paper here. And because this form of MAR, at least when we concocted it about a decade or so ago, wasn't being implemented on a meaningful scale anywhere that we could see, we gave it a name of underground transfer of floods for irrigation, or UTFI. So I'll be using that acronym a little bit in the next few minutes. And what we mean is by that is highlighted in the schematic on the right hand side of the slide, showing that it's basically MAR being done at basin scale to address both seasonal floods and groundwater depletion simultaneously. And so we're dealing with this evaluation using both conventional hydrologic type of techniques, but also looking at it from a gender lens, an economic lens, and a social and institutional lens to come up with a more holistic evaluation of the pilot and the opportunities for scaling up. Next slide, please. Now, before I give you the results, I'd like to deviate a little bit and just highlight a research report that's come out in the last few weeks, where we've evaluated the opportunities for this UTFI at the global scale. It seems like anyone doing a MAR study has to also do a suitability study, and we're no different, and this is at the global scale. And the results are a little bit surprising, showing that around about 600 million hectares of land are deemed high or very high potential for this UTFI at the global scale in every inhabited continent of the earth. And that covers about half the world's population and around about 200 cities with a population of 500,000 people or more. So quite a big potential to implement this if pilots prove successful. And the place of the pilot, I hope you can see it, is the purple dot in the heart of India there, and you can see it's right in the middle of a highly suitable area. Thank you. Next slide. So looking at it from a water quality perspective, we've done the trial over 3 years, 3 successive years, 2016, 17, and 18. And basically the system involves utilizing a village pond, a community-owned pond, and retrofitting that specifically for recharge. You can see a picture of the pond in the bottom right side of the slide. And basically this village pond captures water from a canal that's connected to a river tributaries of the Ganges River. And it's during the monsoon season, when there's an excess of flow, that water is siphoned off from the canal into the pond and recharging the superficial aquifer, which is part of the Indo-Gangetic basin, through a series of recharge wells, a battery of 10, and it's all done passively under gravity. So that's basically how the system operates. And you can see the hydraulic effects in terms of the piezometers there, the mounding that resulted, largely because of natural recharge and partly because of the managed aquifer recharge as well. It was quite difficult to differentiate the effects because of this particular aquifer characteristics. And you see that the recharge volumes that we put into the aquifer varied from 26 to 62 million litres between the 3 years. So significant on a village scale, enough to irrigate anywhere from 8 to 12 hectares of crop in the dry season, or more if it's done on a supplemental basis during the wet season. Next slide, please. And we have also looked, of course, at the water quality intensively. We have about a dozen piezometers scattered around the pond, and we've also sampled household wells and irrigation wells in the area. And we've looked at the results from the point of view of the recharge water, the water that's entering the aquifer, and the groundwater, both within the zone close to the pond that we expect to be potentially influenced by the MAR or the Utify, and also remote from the pilot site, which we call far groundwater, that third cluster on the right-hand side, and looking at the relative percentage exceedance of different constituents. And what this data basically tells us in a nutshell is that the recharge water and the groundwater are very far from pristine. Both of them exceed Indian water quality standards for particular metals and for microbial indicator parameters, but that the near ground water, which is influenced by the MAR, is no worse than the far groundwater, suggesting that the pilot trial has had no net detrimental impact on the water quality in this area. Next slide, please. We also wanted to have a look at what would be the impacts if we were to replicate this on a larger scale, and we chose the Rankgomo basin. It's the sub-basin of the Ganga that this pilot sits within, and it's 19,000 square kilometers, and it's a considerable area. And we simulated using SWOT and ModFlow at that scale scenarios with and without Utify. And the scenarios with Utify had levels of development equivalent to between 10 and 50% capture of the monsoonal runoff. Very large amount of volumes of water, because flooding is such an issue. There are vast amounts of water during that monsoon. To see what would that what effect would that have in terms of the flood risk and also the groundwater levels. And what it showed is that if we did this at sufficient scale, we could see changes in the flood risk, and we could also start to see those declining trends that were evident in the groundwater levels reversing and start to recover the groundwater storage if we did it at scale. And it was quite insightful because we weren't able to see that at the pilot scale because of the small scale and the limited duration of our study of just 3 years. Next slide, please. So sorry, I don't have a conclusion slide as I thought as I should, time being so short, but I'd like to conclude that the pilot looks promising to us. There has been some development take place within the district in which this pilot is established, with it being put into development plans, and we see prospects for further trials in other aquifer and agroecological settings, and perhaps with different types of modalities of MAR. So with that, I'd like to say thank you very much for your attention and happy to take questions.
Thanks, Paul. Well, maybe a very quick question because we're running out of time, but from the audience, there's a quick question on how the suitability of the areas for MAR was assessed on a global context. So the global map that you showed.
Okay. Basically, we looked at a whole host of parameters that looked at the water availability, including the flood risk. We looked at the drought proneness and the aquifer conditions, and we excluded areas where we didn't see floods and droughts. And we basically characterized at a 0.5 degree by 0.5 degree grid at the global scale what the relative prospects. And there's a research report that's publicly available on that's just come out and is available. And if you can't get it, please write to me and I'm happy to forward it to you. Thanks.
Great, thanks very much, Paul. And yeah, I will save my question on the upscaling for the plenary, but it's a very nice and very interesting study that you showed us. So thank you a lot for that. And I would like to ask Jared to invite my dear colleague Tuan to the stage.
Hi, so Tuan Van is a PhD candidate researcher from the Water Resources System Research Unit at the Faculty of Engineering and Chulalongkorn University in Vietnam. I believe he's presenting to us today from Bangkok, and he'll be presenting today on water quality, the impacts and assessment of climate change on groundwater resource development in the Vietnamese Mekong Delta, a case study. So Tuan, I'm going to hand it over to you, and good luck.
Okay, so good evening, everyone. So first of all, I would like to thank to the IWRA to giving me this opportunity to present my research and as well as access many excited topic from the other section as well. And thank the Tibor and the team for running our section very well since yesterday. So my research and my presentation today will focus on the impact assessment on the groundwater resources in the Mekong Delta with the case study in the Vinh Province. So this research is involved in my PhD research, and also from one part of the project on the mitigating groundwater salinity in the coastal area in the Mozambique, Vietnam, and China with the collaborate with the IID Delft. So this research will provide a different view of the impacts of the climate change, indirectly impact of the climate change on the groundwater use in the Mekong Delta. So next slide, please. So in the Mekong Delta, you can see in the picture in the right-hand side, so the landscape, one landscape of the aquifer system, about the surface, flood, the sea, and many structure land use. And for the groundwater use, the first problem is the limited of the fresh surface water with a lot of dam construction in the upper of the Mekong Delta, and we have the reduction of the rainfall by the different climate change, and we have the increasing the water demand in the Mekong Delta with the developing in the industrial supply sector. That's why the groundwater has been becoming the over attracted, and groundwater issue now focus in treating the first thing that disruption of the groundwater, and many like in the city of the Mekong Delta we face with the extremely depletion of the groundwater like in Vinh Province, Kancher, or the Khmer province. The other thing is about the saline water intrusion, and the last one is the land subsidence due to the groundwater depletion as well. So how to achieve the sustainable balancing between the demand and the supply water in the Mekong Delta has been becoming a major challenge. Next slide, please. So in this research, we try to estimate the future groundwater demands by different the societal and economic scenario, and as well as the climate change scenario. And based on that, we use the model to assess the impacts of the groundwater demand on the groundwater levels, storage, and also the salinity movement. And the study area we select is the Vinh Province, located in the coastal part of the Mekong Delta, in the between of the two main contributions of the Mekong River in Vietnam part. So the area is covered around more than 2,000 square kilometers, and it's one of the highest vulnerability area under climate change in the Mekong Delta. And this province It's also one of the poorest provinces with the main economical activities, the agriculture and aquaculture. And one thing about this province, the available of the fresh surface water, it mainly depend on the upstream discharge and also the tidal. So you can see in the picture is the area of the Chapin province. So here we separate the area to 3 zones. So in the coastal zone, the fresh the saline water is available in the whole year. And in the northern zone, fresh water is available in the whole year because they have some sluices to protect the fresh water. And in the middle part, it's quite flexible. It mainly depends on the year, water year, like a high discharge in upstream or lower discharge in upstream. So by separate treating, we compare with the potential of the groundwater to see what the impact of the climate change by different zones. Next slide, please. So here we select 2 or 3 scenarios of climate change represent for 3 GCMs of the medium emissions, RCP 4.5 to carbon waste of the climate change in the lower Mekong Basin to 2030 by the Mekong River Commission in 2016. So the first one is like a Rooyen model, and the medium model and the wetter model represented by 3 GCMs. And beside that, we also select the 2 socio-economic scenario. The first one is the business as usual. We try to keep the developing as the trend of some recent years by following the local plan. And another scenario is to try to follow the master plan of the whole Mekong Delta with a lot of change of the infrastructure, structure of the land use, and some improve in the water supply. So you will see in the detail of the table separated by the 6 scenario by combination of the 3 climate change scenario and 2 social and economic scenario. So next slide, please. So in order to estimate the groundwater demand in the future, firstly, we should the statistical data of the salinity distribution in this province and also the upstream discharge in the upper part of the Mekong Delta. So the statistical data show the very good correlation between the upstream discharge and the salinity distribution. So with the low discharge in the upstream, so we have the more days of the saline water distribution in this province. So we should the function by the correlation between the discharge and the saline, the duration without the fresh water in this province to simulate the duration without the fresh water in the next decade. So here we use the first table, we use the prediction result from the MC in 2016 to estimate the average discharge in the next decade. And after that, we have the survey in the province to estimate the proportion of the groundwater use in the dry and wet season compared with the total use of the water by different zones. So for the domestic and the industrial use is not changed by the different scenario, but for the agriculture and aquaculture, the duration of the fresh water and saline water is a difference between the scenario of the climate change. So you can see by the drier expectation of the climate, you can see the percentage of the groundwater use compared with the total water use is around 35%, 71%, and 100% following the northern, middle, and coastal zone respectively. And but for the western expectation of the climate change scenario, the percentage is quite much larger. So at the end, we estimate the change of the groundwater demand compared with the base year in 2018. So you can see the difference between the 2 scenarios of the social economic scenario. So with the business as usual, when we try to keep the activity of the agriculture and aquaculture as the current time, so we see the increasing of the groundwater pumping by even different scenario of the climate change, especially in the drier expectation of the climate change, the groundwater demand was estimated to increase more than 2 times. However, with the following the Mekong Delta plan, the groundwater demand seems to reduce a lot, especially for the wetter expectation of the climate change is the reduce more than a half. So next slide, please.
When you have one more minute, huh?
Yeah, after that, the groundwater demand was the input to the pumping package of the flow model and MT3D model to simulate the groundwater level and as well as the salinity movement. So you can see this here, this picture. So the groundwater level distribution in the March of the 2018. So the red one shows some definition in of the third aquifer. It means the main aquifer contribute about 70% abstraction of this grouping. So one more click, please. Yeah, so we can show the three first scenarios. So with the maintain the agriculture and aquaculture activity. So water level still decline, be 4 or 5 meters after the next 10 years. So next, please. However, with the reduction of the groundwater pumping by following the Mekong Delta plan, so you can see the increase of the groundwater level. So next slide, please. And we also see the difference between the saline water area extension by different scenario. So the you can see the a little bit conflict. The saline water is distributed in the inland, in the northern part, not in the coastal part, because some the regression or chance regression in the past. You can see in some other public explain about why the saline water distribution in the Mekong Delta.
Tuan, so we will have to end. Let's go to your wrap.
So
one sentence
my
presentation.
So we can see the with the changing the land use pattern by following the Mekong master plan, you will need the groundwater demand to meet the sustainable use of the aquifer system by the current pumping. And if we maintain the current activity of the agriculture and aquaculture, groundwater level is still decline and saline water still increase by 10 to 70%. Thank you for now time a little bit. Yeah.
Thank you, Tuan. Yes, we will have to move on, and so there will be questions for you for in the plenary following the last talk. But anyway, a very important topic, and understanding that MAR is not maybe a solution everywhere, and that we need to look at reducing groundwater demand in some cases to be able to recover some of our problems that we have. Yes, let's move on to Enrique, Alvaro Enrique Fernández Escalante. He works at the TRAXA Research and Development Group in Madrid, and he's also the chair of the IAH MAR Commission for the International Association of Hydrogeologists. And Enrique will talk about water quality regulations and guidelines for MAR, working on an international synopsis and contrast and lessons learned. Enrique, please, the floor is yours.
Thank you very much, Tibor, and congratulations to the whole organization of this outstanding conference. I am enjoying it really very much. And also our gratitude on behalf of the IAH MAR Commission for having included MAR as a federal topic in the conference. Next, we are going to benchmark 18 different regulations all around the world regarding MAR water quality, no quantity. Callum, could you please pass the slide? Yeah, thank you. MAR is a set of techniques to improve integrated water resources management. And it has gaps for MAR implementation. And one of them is the clear regulation regarding its implementation in different countries. The early MAR countries usually adopt the WHO guidelines as a lighthouse for any project. And in this presentation, we are going to benchmark 18 different regulations. Next, please. So by 2014, and by means of the IAH MAR Commission Forum, I started requesting to the colleagues the regulations from their different countries. It has been complemented by Google Alerts and plenty of internet searches. And finally, we have gathered 18 different, let's say, regulations. They have been studied, compared, identifying the differences weaknesses and strengths, not only for the water quality point of view, but also from the economic, environmental, technical, and scientist. Next, please. So this is the set of countries analyzed, and either the regulation could be at national, local, state, or regional level, and some of them are developing the regulations right now. Next, please. So we have conformed this 10-10-10 table first, in which then there are displayed the 18 different countries, the scope. Either they are a soft or hard measures, the type of regulations. So in some cases, there are guidelines or even operator rules. Of course, these operators have capacity to regulate somehow. The year of the specific regulation and the 10 which have max, what is to say the maximum allowable concentrations published in their reports. Finally, the most employed. Passing the slide, it is the habit. Next, please. Meters per regulation. In the top ranking is the USA, of course, and the Trump law from the previous year considers 149 different compounds and parameters. And in detail, there are the state of Florida and Spain with 4 and 6 respectively, but for SATMAR, not specifically for MAR. Next, please. And this is, from our point of view, an important contribution for the whole community. And it is a table incorporating all the regulations and the max and the ranges of tolerance of 10 different countries and the whole set of parameters exposed in any one of them. So the total amount of parameters regulated are 255. Next, please. Starting the benchmarking, there is a comparison between the different max. The parameter, the compound most regulated is the nitrates concentration. It is 6 out of the 10 studied laws. Secondly, the total nitrogen and the total dissolved solids in 5 out of the 10 countries. And just to bring up some examples regarding the TOC, the organic compounds, in Florida, there is a limit of 1 milligram, whilst in Mexico, it is established in 16 milligrams. In the total suspended solids, in Florida also, it is below 5 milligrams, whilst in Mexico, it is established in 150 milligrams per liter. Regarding the total nitrogen, the highest MAC is also in Mexico with 40 ppms, and the lowest in California and Spain with 10 ppms. The total phosphorus, there is a huge cliff between Mexico and California, and Belgium, sorry, with 2 orders of magnitude. Regarding chlorides, the limit in Mexico is 300 ppms, and in California, 120, 2.5 times more. Talking about sulfates, in Mexico, again, 300 milligrams per liter, California, 125. Regarding turbidity, the highest MAC is in the Israel standards with 10 NTUs, and the most strict in Spain with 2 NTUs, in this case for direct injection, 5 times more. Regarding heavy metals or metalloids, in Belgium and the Netherlands are the strictest. For example, for the zinc, and there are 200 micros, and in California and Mexico, 5 milligrams, 77 times more. So the most regulated heavy metals are arsenic, cadmium, lead, and mercury, with the MAC reported in 7, more even than nitrates, water quality standards. Also, the Mexican regulation is the most permissive regarding MACs, when the most restrictive are in special Spain and California. Next, please. And also, there is another result, one advice of the total amount of compounds and parameters that should be analyzed in any MAR project. This is a contribution, of course, to be decided by each technician. Next, please. Jumping into the discussion, the MAR parameters regarding water quality standards depend on multiple factors, such as the MAR technologies applied, the environmental conditions, and the final use, of course. It is also important to mention the lack of a common terminology. People are talking about managed aquifer recharge, artificial recharge, intelligent aquifer recharge. We need to be concentrated in the key target, what is to get the message through in terminology. Also, a consensus for rules and process to grant permissions will be a good thing, especially thinking about transboundary aquifers. The methodological approach and recommendations to achieve a monitored recharge under a common instruction, and the need for a broader legal development. Regulators, decision makers must regulate looking around. And next, please. And regarding recommendations, every approach should be aquifer-wide. It is, in my opinion, a madness. A common regulation for a country with 500 different aquifers. So they should consider the hydrogeochemical criteria, the MAR technologies, either infiltration basins, flooding, runoff, the final use, irrigation, drinking water, of course, should be more strict in the case of urban water supply than for irrigation, for example, and concrete monitoring guidelines, considering the cost of analysis, sampling frequency, and the exact point to gather each aliquot. Next, please. Landing into the conclusions, a distinction must be made depending on the type of recharge with different limits for each case. I am repeating because it is really important, in my opinion. Tailor-made water quality guidelines should be performed for each specific aquifer. Independent control and surveillance mechanisms will be an asset, not leaving to the government or the monitoring. And finally, a risk assessment should be considered for each MAR policy. These recommendations are supported in this article published this summer in the Italian Journal of Groundwater. Next, please. Just to make the best of the half minute that I have left to invite you to participate in the IAH MAR Commission Forum, where there are plenty of synergies between the whole participants. And the last slide, please, Callum. Just to inform and remind, there is a WhatsApp group with 150 members debating of MAR issues. And there is the imminent UNESCO release of a book of 28 international MAR case studies entitled Managing Aquifer Recharge, a showcase for resilience and sustainability. Probably Alisa Aureli will have a surprise this evening for all of us. I wish, but I'm not sure. Thank you very much. Sorry for these 10 seconds.
Thank you, Enrique. Indeed, running out of time, but a very quick question. When you say guidelines should be aquifer-wide, do you mean, what do you mean? Is that your opinion, or is that something that you found from the literature?
Yes, of course. It is the result of the benchmarking of all the different regulations. It is a mess. They are applying specific marks for aquifers that don't deserve that limitation, because the purification capacity is higher than for a karst. The regulation is common for the detritic or for the karst. It is a madness currently.
I understand. Yeah.
So
it's very nice that you have showed that in your overview, and we might come back in the plenary. But I would like to thank you and pass it on to Jared to invite our last speaker.
Thank you, Tibor. So our last speaker is coming to us from Hungary. Tibor is a hydrologist and a PhD student at the Department of Geology at the Eötvös Loránd University in Hungary. And today she's going to be talking to us about the preliminary results of rooftop rainwater harvesting and shallow well infiltration, a pilot project in the Danube-Tisa interfluve. So Tibor, over to you and good luck. Thank you.
Okay, thank you, Jared. Very nice pronunciation, so thank you. So I'm Zsóka Szabó, and let me introduce you our preliminary results regarding this experimental pilot project. Next, please. So due to climate change, weather conditions are becoming more extreme also in Hungary. So we have negative effects here as well. And these are affecting the environment and agriculture in this area. And these are causing, of course, social and economic problems as well. And as we could saw during this session, MAR can be a suitable way to reduce these extremities that are happening more frequently now. And our research aim was to find local scale solutions in our study area in the Danube-Tisza interflow and evaluate how MAR can contribute to the water shortage of this area. Next, please. So the study area is located in central Hungary. It is a rich region between the Danube and the Tisza rivers. It's composed of alluvial sediments and aeolian sands mostly. And the water level has decreased in the past decades remarkably, partly due to climate change and partly due to artificial reasons like water abstraction and drainage channel constructions. So we have these problems with water level drawdown, which are affecting groundwater dependent ecosystems and the agriculture in the area as well. Next, please. For example, you can see here Lake Condor, which has dried out 30-40 years ago in the area due to the water level drawdown because it is groundwater fed, or it was in the previous years. And there were many replenishment plans in the area, but unfortunately none of them has materialized. And one of the recent plans was to move water from the Danube to the center of the reach through the existing channel network and replenish the lakes here. But it would be too expensive to do that because you need to pump the water up to the region. It is higher elevated. And the water chemistry is also different because river water from the Danube is completely different than what we have here in these groundwater dependent ecosystems. So we were thinking on using MAR here because it is a nature inspired method, and also rainwater collecting would be a better method here in the area. We did a suitability mapping and we found suitable areas here, where you can see the rectangle on the map. And this is where we started our pilot project. Next, please. So you can see here our experimental pilot site. And the source water is rainwater collected from the roof of this family house. It is located in an agricultural small town. And we are using filters before the water reaches the tube system. And we have here an unconfined shallow aquifer with sand mostly, and low water table. The shallow groundwater is mostly it has high TDS around 1000 milligram per liters. And this is not really used by the residents anymore due to the contaminations, and also because most of the wells have dried out in the past decades, most of the shallow wells. So we are using this well in the yard for infiltrating water, and we also constructed 2 monitoring wells, and we are measuring water level, electric conductivity, and also temperature in all 3 wells in this pilot project. Next, please. I would like to show you just some results due to the time limit. You can see here the water level changes. The preliminary results are very encouraging. In the first 2 months, which you can see at the beginning of the data set, we had lot of rain in February, and you can see the sharp changes in water level in the infiltration well, and you can see gradual infiltration in the water levels. However, we had 2 months of drought in March and April, and after that, the water table started to decrease again in the monitoring wells, which you can see by red and green. And we had rain during the summer, but this couldn't compensate for the water level decrease. Next, please. In the electric conductivity data, with blue you can see the infiltration well, and you can see that the values are decreasing due to the infiltration, which is good. This is what we expected. And after every period without rain, it is increasing again a little bit, but it won't go back to its original value. So now it decreased to half of the first measured value here. However, in the monitoring well, especially if you could see the red line, the electric conductivity is increasing. It's probably due to the fact that we are infiltrating water, and this infiltrated water amount pushes towards the groundwater to the monitoring well, and this is the groundwater. As I told you, it has high salinity, it is contaminated, it's an agricultural area. So we are trying to achieve natural attenuation here, and we expect that this increase will stop and will start to decrease, as we saw the decrease also in the filtration well. Next, please. In the infiltration well, we took several samples from the infiltration well, and the TDS, the chloride, the sulfate, the nitrate content is decreasing remarkably during the infiltration, and also magnesium content decreased, and calcium starts to dominate in the samples. However, in the monitoring wells, we took samples after 8 months from the start of the project, and TDS is higher, and also magnesium content is very significant. So it is quite similar to the composition of the first samples from the infiltration well. So this is well corresponding to the observations of the electric conductivity data. Next, please. The temperature changes are very nice. They are showing seasonality. You can see that in the beginning, infiltrated rainwater is causing temperature decrease, but after May, and the relationship starts to invert, and the water temperature increases with every rainy event. So, and in the monitoring wells, we can see a lag time. The water temperature is decreasing, but after June, it starts to increase. So we have a nice seasonality here in the groundwater data. Next, please. So as to conclude, what we have here, in the first 2 months, the water table increased with 20 centimeters, and it was only just a small amount of infiltrated water. And after this increase, we had a longer drought in the spring, and it started to decrease again. But I would like to highlight that in this area, the groundwater tables are continuously decreasing. So as a first step, it would be even good to have a lowered rate of decrease, or even a stagnation of water level. It would be a huge achievement to invert the decrease of groundwater tables here. And the TDS, the chloride, sulfate, and nitrate content decreased remarkably in the shallow well, and we are expecting natural attenuation here. So we are hoping that this decrease will show in the monitoring wells as well. And in the future, we are planning to have more detailed geochemical, hydrochemical data from the shallow well and monitoring wells, and also from the rainwater and the water reaching the well from the PVC hoses or the tubes. And we would like to continue this pilot project for at least one hydrological year, but preferably more if it can happen. And we are planning flow and transport modeling to understand better the processes occurring underground. We have some results already, but we are trying to extend it to the whole data set. And our final aim is to extend the results of this pilot project to the whole settlement. And
Follow, we need to continue, but just finish your sentence, please.
Just the final sentence. So our aim here is to extend the results to the whole settlement with a settlement scale modeling study, including more wells in the area. And our aim is to make a feasibility study and evaluate the feasibility of rooftop rainwater harvesting and shallow infiltration here to cope with water scarcity and climate change in this area. Thank you for the attention.
Thank you, Joka. We need to move on to the plenary, which is already quite reduced in time. So let's see. Thank you, thank to all speakers for your nice talks on largely linked to this topic of MAR and its potential for remediation of groundwater through attenuation and dilution. Jared, are there a number of questions that we could still pose to well, each of the speakers? And I see that there have been a number of answers already, also by speakers, written answers. So thank you for that as well.
Yeah, thanks guys. You really helped out getting the questions down. So we have 5 open questions still. Tsoka, I think I'm going to stay with you for now, just so we can have a continuation from your talk. David asked, what impacts of climate change are expected in the precipitation, and how would they affect the collection of water for the subsequent managed aquifer recharge? And would this compromise the efficacy of the pilot project?
Okay, thank you for the question. Actually, we are expecting maybe a small change in the amount, but mostly in the, not in the amount, but mostly in the distribution of precipitation. So that's why we're saying that collecting rainwater would be good here, as we would need to gather all the rain that we will have in the future. So we will probably won't face a huge decrease in the water amount, but the distribution will change.
Okay, perfect, thank you. And then just one more quick question. Atish asked if there's been any response time studies done on the project, the time from the rainfall event to the increase in groundwater level, I suppose like a hydrograph separation of sorts. Have there been any other studies?
Yes, we have started, and I forgot to mention, but we calculated that the water reaches from the infiltration well to the monitoring wells, it's just 10 meters or 12, and it reaches the monitoring wells in 3.5 days. So we have a very good connection here, and actually we don't see any signs of clogging yet, but we are using actually cross correlation calculations to evaluate that.
Perfect, thank you so much. I suppose moving on as quickly as we can. Hafsa, we have, I think, 2 questions still outstanding from your talk in the beginning. The first one being the consequence, I'm just going to summarize this quickly, of the novel coronavirus, its potential impacts in these shallow reserves. Is there any kind of thoughts that you have on the issue, just coming from Mohammed?
Thank you for the question. Well, I think I don't know much about the coronavirus because it's more microbiological pollution sources. So I don't think so I would be the right person to answer this question.
Okay, perfect, thank you. And then I see that the other outstanding question has been answered already.
Yes.
So we only have 2 left. And let me just make sure I get them for the right person here. So Teresa just had a comment that I think had to do with Enrique's presentation. And this was just talking about the Mars Solute H 2020 project and something for you to look at. And I don't know if you'd care to comment on this quickly, Enrique, before we move on.
Yeah, we are working on standardization and interoperability among the different groundwater sensors. They are speaking different language, and the common terminology, Esperanto, let's say, should be required for all the different monitoring devices to be interoperable. So this is an open line of action, and in 2 years, we expect to release the results.
Then I suppose just like rolling on from that, sorry, Tibor, just talking about areas that have not the resources to potentially implement these kind of plans, and this is coming from Mohammed Manani, just some comments on, you know, technical support, the training needed, particularly in areas like Africa. Would it be possible to implement this, and what would be needed to give this infrastructure and information for places like this?
This is the question for
Enrique. Yeah, it's still going on with this. The guidelines. Yeah, would we be able to implement this in places like Africa where the resources aren't as large?
Feasibility of implementation in Africa of these kind of stricter guidelines.
I'm sorry, I have understood it was for Mohammed, not for me, the question. Very sorry. Yes, there are huge possibilities. At this moment in Argelia, for example, they are developing a new implementation near Oran, and I have heard of plenty of studies regarding not only in cooperation projects, but also developed by the own states.
Thanks.
Okay, that's Jared. All from my side, Tibor.
Okay, I do make misuse of my position for one final question to Paul. Paul, my typical question regarding upscaling is, how would you see the need for the size and number of basins and ponds, basically, if you really want to take care of effectively reducing these kind of floods? Have you, have you put some thoughts into that?
Thanks, Tibor, for the question. Yes, of course, we've thought about the upscaling potential, especially in the Gangetic Plain, which is one of the most populous and intensively utilized areas for agriculture in the world. So lands at a premium, high value, socioeconomic value. So using these village ponds, the community-owned ones, because rather than the privately owned ones, present the best opportunity to us, because these are largely unused as farmers and communities have moved away from pond water supplies to private groundwater wells. So they're largely defunct, and they're in the district we're working on, there are 1,800 of them. So a huge potential, probably enough to do a large amount of scaling. Now, it's not to say every pond's in a suitable area, it's well connected to a source, etc. We have very strict criteria in terms of what is an ideal site, but there is lots of potential for scaling up in our view. And there's also what they call wasted land as well. So lots of opportunities, and we've done some mapping and assessments of those too. Thanks for the question.
Great, Paul. Yeah, and also very interesting to see how that could, for instance, help also lower arsenic concentrations, which I think is also has a high potential through your method. But we do need to end. Unfortunately, we could go on, but there's a next session waiting already. And again, thank you all for this great session and your talks. Thanks, Jared, for really professionally bringing us the questions. And well, I'll see you all very soon in the next session for sure as audience. Thanks once again, and talk to you soon.
Thank you very much, coordinator.
Thank you very much.
Thank you, everyone.
Thank you very much.
Thank you all. Bye.